Here we've got some basic notes that should be a review from physical science and from chemistry last year. The definition of energy, this equation for energy may be new to some of you. So go ahead and make sure you have this copied down. E equals Q plus W. Q is heat, W is work. The units, kinetic energy. Notice kinetic energy is M, which is mass, and V, which is velocity. So when we're talking about kinetic energy, we have to consider both the mass of the particles and the velocity of the particles. One of the key ideas here is that heat and temperature are two different things. We use them interchangeably outside of chemistry all the time, but really temperature is a measure of the kinetic energy of the particles in a sample. Now it doesn't mean if two things are at the same temperature they're moving the same speed, because something might be more massive than the other. But they have the same kinetic energy, so the more massive ones might be moving slower, so when you multiply those together in the formula, you get the same temperature as smaller particles moving faster. In either case, same temperature means same kinetic energy. Heat, on the other hand, is the energy that increases the kinetic energy, increases the speed of the particles. You're not going to introduce heat to make the particles bigger. So heat is the energy that increases the speed and the kinetic energy, which then increases the temperature of the sample. Which brings us to the first law of thermodynamics. Simply put, and this is the original way it was stated, the first law of thermodynamics says that energy is conserved. The way you learned it in the past was that energy cannot be created or destroyed. It means the exact same thing. If E is the internal energy of something, we can't measure E of anything. I can't pick up a beaker full of water and say, tell me the internal energy of this water. What I can do is measure the change in energy, delta E of the water. Remember delta, the triangle, Greek letter delta means change. And I just take the final energy minus the initial energy. Well, how do I do that if I can't measure the energy of either state? Well, I can look at the heat that flows into it, which is Q, and W, the work that it does. Because if you remember, the definition of energy is the ability to change heat or to do work. Now this is something called a state function, and we need to talk about state functions real quickly here. A state function is anything where the path doesn't matter. All that matters is your starting point and your ending point. So let me give you a bit of a metaphor. If you're hiking up to the top of Paris Mountain, and I wanted to measure the change in altitude from the bottom to the top, it doesn't matter what path you take to get there. If you walk straight up the mountain from the bottom to the top, your change in altitude is exactly the same as if you followed the windy trails to get from the bottom to the top. Because it doesn't matter which path you took, that becomes a state function. Energy is a state function. It doesn't matter how many changes it goes through. If you know what the energy was where it started and what the energy was where it finished, the number of steps to get from start to finish doesn't matter. All that matters is what your starting point was and your ending point was. We're going to talk about several things that are state functions as we go through these notes. Thermodynamics and state functions are very tied up with each other. However, if you've had calculus or you're taking calculus, it might interest you to know that the path you follow is actually the integral of the state function. If you haven't had calculus, don't worry, that won't make any sense to you, and that's fine. Just know energy is a state function. It doesn't matter how many steps you take, all that matters is where you start and where you stop. So if we take a look at the signs from that equation, if Q is positive, Q is heat, that means the system is gaining heat. Heat is flowing into the system. If Q is negative, heat's flowing out of the system. The system is losing heat into the surroundings. If W is positive, that means work is being done on the system. Work happens when movement occurs, force through distance. So if work is done on the system, that generally means the system is being compressed. Okay, if it's a gaseous system, it's being compressed. If W is negative, that means it's pushing out against its surroundings. It's inflating or expanding and pushing out into its surroundings. So if we add up Q plus W, if they're both positive, delta E, the change in energy will be positive. So the whole thing is gaining energy. If they're both negative, the whole system is losing energy to the surroundings. If Q and W are different signs, we just have to look at which one's bigger. If overall it's positive, if the positive is bigger than the negative, then the system is still gaining energy overall. If it's overall negative, then the system is losing energy overall. So you have to look at how much heat is being put into a system, how much work the system's doing, add those things up to find your delta E. We're going to be dealing specifically with something called pressure volume work, and that's when gases are expanding or contracting. pressure is put on the gases, and we measure the volume. And we do this at constant pressure. So the pressure isn't going to change. There's no delta P, no change in pressure, just whatever the current air pressure is. We're going to measure the change in volume. And so the work is the negative of pressure times the change in volume. Why negative? Well, look at the signs. If the gas is expanding, that means the change in volume is positive. It's getting bigger. Well, that meant that the system was losing work. Remember, when it was pushing out against the surroundings, that's doing work on the surroundings. Energy is going out of the system. So if delta V is positive, W has to be negative. So we have to make it negative P delta V. And same with the opposite. If the surroundings are doing work on the system, the volume is going to decrease. It'll be negative delta V. So the work has to be positive for that, because the work is putting energy into the system. Let's take a brief side trip here and remind ourselves about endothermic and exothermic. Endothermic is when the system gains heat. Endo means into, therm is heat, and that means it's coming in from the surroundings, which means the temperature of the surroundings is going to decrease. Because if heat is leaving the surroundings, heat causes temperatures to rise. If heat is leaving the surroundings, that means the temperature is going to drop. So when you hold an ice cube in your hand and the ice cube starts to melt, your hand is going to feel cold because heat is going out of your hand into the ice cube. The opposite is true of exothermic systems. The system is losing heat. So burning a match feels hot when you put your hand near it because the heat energy is leaving the system of the match and flowing out towards your hand. So the temperature of the surroundings increases. Here's the diagrams I want you to sketch into your notes. Notice for exothermic, the reactants are higher energy than the products because it lost energy to the surroundings. And so the products end up with lower energy, less energy than the original reactants had. For endothermic, it's the opposite. The products have more energy, which they must have absorbed from the surroundings outside. Pause the video here, copy these into your notes. Make sure you get the axes in there. Enthalpy, then, is described as the flow of heat at constant pressure. We do have heat flow at non-constant pressures. We'll get to that in a little bit. But we're only going to deal with pressure-volume work here, constant pressure work. So enthalpy is given the symbol H because it's heat. We'll get to that in a second. The equation is enthalpy is energy plus pressure-volume work. In other words, if we take the change in enthalpy, that's equal to the change in energy plus pressure, no change in pressure because it doesn't change, times the change in volume. This is a state function. It only matters at the beginning and at the end. Let's substitute. Delta E is Q plus W. I substitute that. P delta V is the negative of work, so I substitute that. Then I'm going to combine and simplify. Q plus W plus a negative W, well the W's cancel out. Delta H, the change in enthalpy, is equal to the heat change, Q. That's very important for our next equation. Take a look at the sample problem, read it, try to answer it. We'll talk about the answer in class. Pause the video here while you write your answers in. Welcome back from that sample problem. When we look at the enthalpy of a reaction, a chemical reaction, the change in enthalpy is the enthalpy of the products minus the enthalpy of the reactants. Always products minus reactants. Everything's be products, which is final, minus reactants, which is initial. That's how we always do it. So in the sample equation I have here, I've got hydrogen reacting with oxygen to make water. I don't know why the arrow got replaced by a box. I'll look into fixing that. But the way we draw it as a diagram is we draw a horizontal line for each step in the reaction. The first step, the reactants are hydrogen and oxygen. Those are higher energy than water. We know it's an exothermic reaction. It gives off energy. You've seen the video of the British guy where he burst those hydrogen bubbles and they made the nice little fireball. Exothermic reaction. So the products have to be lower than the reactants. And we draw a second horizontal line, the other red line, for the water. And we draw an arrow going down, showing that the energy of the system decreased. It's exothermic, energy of the system decreased. Copy this diagram into your notes. Some basic guidelines to keep in mind here. Enthalpy is extensive, meaning if you double the amount you're starting with, you double the heat. And that makes sense. If you have twice as much hydrogen and oxygen, you're going to get twice as big a fireball. So we usually look at how many per mole that we use. Point number 2, the enthalpy change is equal but opposite sign for the reverse reaction. So if we took water and we split it into hydrogen and oxygen, we'd have to put in that much energy. The same energy we got out of the system is how much we'd have to put in to reverse the reaction, assuming the reaction's reversible. And there are some that are not reversible. Point number 3, it depends on the reactants, the state of the reactants in the products. So if we're making water vapor, H2O gas, we'd have a different value than if we're making liquid water, H2O liquid. So we have to keep those in mind, always write them, always check them when you're getting your numbers from the back of the book. Look at the sample problem. You've got grams of methane. Think about what's the first thing you do to grams if you've got grams in a problem. I give you a value there. See if you can figure out the kilojoules of heat released when that much methane gas is burned. Pause the video, solve it. We'll solve it together in class. Welcome back to the sample problem. Calorimetry is a measurement of the flow of heat. Calor means heat, metry is measuring, and the instrument we use is the calorimeter. And we'll talk about calorimeters in a little bit. Heat capacity is how much the temperature changes when you put heat into something. So if I dump 100 kilojoules of heat into water, we can measure the temperature change of water, and that rate is its heat capacity. If I dump the same amount of heat, 100 kilojoules, into the same amount of iron, we can measure that heat change. And actually the iron will change more than the water does. Water has a higher heat capacity. It takes more heat to change the temperature of water than it does to change the temperature of iron. Heat capacities are expressed per mole. Whereas if we express it per gram of water or per gram of iron, we call that specific heat instead of heat capacity. They measure the exact same thing, one's per mole, one's per gram. So be careful with your nomenclature on this one, heat capacity or specific heat, but for the calculations, just look, do I have grams, do I have moles, what do I need to change it to based on the numbers I'm given? And here is the equation for specific heat. It's also the same equation for heat capacity, but instead of M for mass in the denominator, you'll use moles. So for specific heat, S equals Q over M delta T. Heat, energy, divided by grams and the change in temperature, and that would be in Kelvin. If we're doing heat capacity, we use C instead of S for capacity, and that's Q over moles times change in temperature in Kelvin. Use that formula I just gave you, the specific heat formula, and solve this problem. We've got grams of water, and I give you specific heat, which is in grams, so we don't need to change it to moles right now. Calculate that energy change, and then go through, and so we're solving for Q in the first part, and then figure out the molar heat capacity. So all you have to do is take the Q that you've solved for, the joules, and divide it by the number of moles of water you had. We'll go over the answer to this together in class.